Hello, and welcome back to another IB Math Speedrun with me, Vince. In today's speedrun, we're going to be going over Chapter 5.3 of the textbook, which talks about some statistical techniques that we can use to analyze data even further. So let's jump right in. So the first thing we need to talk about is a box and whisker diagram. And to do that, we need to remember, our interquartile range and our range. So if we arrange our set of data in order, let's say we have, we have 1, 2, 3, say we have, 8 different terms, say 2, 3, 4, 4, 5, 7, 9, 9, and we arrange them in order. The interquartile range is the difference between the first quartile, 3.5, and the second quartile, which is, in this case, 8. And the median is 4.5 here. But if we want to arrange this on a box and whisker diagram, what we can actually do is let's draw one properly. We can arrange these values on a plot of their actual values. So if we label this as 2, 3, 4, So first we need to draw a whisker from the minimum to the interquartile range, to the first quartile. So we go from 2 to 3.5. And then we draw from here a box. So something that looks like this. And then next we have to go from this box all the way to the median, so 3.5 to 4.5. This will be the median. And next we go from this box, which is 4.5, and we need to go to 8. So 5.5, 6.5, 7.5, 8. So this is the other side of the box. And finally, we draw a whisker from the third quartile to the final value. So from 8, we're going to go to 9. So simply looks like this. So yeah, this would be a box and whisker plot of this diagram. This value is 2, 3.5, 4.5, 8, and 9. And it gives us a representation of both the range, which is the total length of the entire diagram, and the interquartile range, which is the difference between the first and third quartile, or the two sides of the box. And so this can be very useful in detecting if we have lots of outliers, just in a visual way. Yeah. Next, we need to talk about variance and standard deviation, which is the third way of measuring the spread or dispersion of a data set. Because, the range and quartiles are good measures, but they don't use all the data values to give an indication of the data spread. They only use the certain either minimum or maximum, or values that happen to be in the first and third quartile. And to get one of the most accurate ways of measuring the spread is something called the standard deviation. So the standard deviation gives you a mean average of the distance between each data point and the mean. And so we use the, I think it's rho, or do this Greek symbol to signify standard deviation, and this is equal to the sum from the first data point to the last data point of that data point minus the mean, where remember mu is equal to the mean, squared over n, where n is the number of data points. So this is standard deviation, and variance is equal to standard deviation squared. And so we represented with, I think, rho squared, and so this is just simply equal to the mean average of the squared distance between each data point and the mean. So this is the sum as I is equal to 1 to n of x minus the mean squared all over n again. So if the data set is very close together, then the standard deviation and variance will be quite small, but if it's quite spread out, then the standard deviation will be quite large. And the units of standard deviation are the same as the units of the original data. Okay, with that being said, let's jump into some questions where we can apply our knowledge. So I will be doing, let's see, what questions do we have here? What looks hard? I guess I'll do the even ones. They look a bit harder, so let's do the even ones. So first, for a particular data set, the following summary statistics were observed. So the sum of the function is equal to 20. Oh, so the number of terms. Actually, let me write it out in the statistical notation. So we need to find the values of the mean and the standard deviation squared. So the first thing we note is the sum of the function, which is the sum of the number of values, is equal to 20. So there are 20 terms in the set. Next, the sum of the actual function of x is equal to 563. So if we add up all, this means if we add up all the terms, sorry, not function, more of that. If we add up all the terms, we'll get 563. And finally, we're given the sum of the squares. So that's equal to 16,143. So this means if we add up all the squares, then we will get 16,143. So first, what is the mean? The mean is simply the sum of the terms over the number of terms, 563 over 20, which is 563 divided by 20 is equal to 28.15. So the mean is equal to 28.15. Now next, the standard deviation. So we need to find the standard deviation, and this is a bit harder. So we know this is equal to the sum of the terms to n of x minus the mean squared over n. And the thing is, there is a little trick you can use here. And the trick is that this is actually equal to the, this is equal to the sum of the squares minus the square of the sums, I believe. So what I mean by that is that this should be equal to the sum from n to I equals 1 of the x squared over n minus mu squared. Yeah, sorry, I'm back. I just made a small mistake. This is actually just over mu squared because, yeah, so how you remember it is it's the average of the squares minus the square of the average. That's how I like to memorize this formula. So if we have, this can also technically be rewritten as the sum of fx squared over sum of f minus the sum of fx over the sum of f squared. So in our case, this is equal to square root of 16143 divided by 20 minus the mean squared, so we have 28.15 squared. So this is equal to 16143 over 20. So 807.15 minus 28.15 squared. So I get the square root of 14.7, and so our standard deviation should be equal to around 3.838. So it should be around this value. So that's the standard deviation, and this is the mean up here. Yeah. So we're cool with that. So now we can move on to the next question. Let's just check the answer is right. Yep, okay, that's correct. So next question, and actually final question, quite a short chapter, is we need, we have samples. Write it out. Oh, not that. We have samples of water were taken from near a chemical plant to see if the lead content is too high. The following data was collected in micrograms per liter. Use this data to predict the mean and standard deviation of the sample, and it is said that over 10 micrograms per liter of lead in water is deemed a dangerous amount. Comment on whether there are grounds for further investigation. So the samples we are given is 6.3, 9.6, 12.2, 12.3, 10.3, 12.1, 10.3, 8.4, 9.2, and 4.3. So these are all the samples. So let's predict the mean. The mean would be the number of the terms over the number of terms. So 6.3 plus 9.6 plus 12.2 plus 12.3 plus 10.3 plus 12.1 plus 10.3 plus 8.4 plus 9.2 plus 4.3. So the sum of the terms is equal to 95, and there are 10 terms in total. So our average would be 9.5. So mean is equal to 9.5. But let's also get the standard deviation. So to do that, we square each term. I'm not going to show the squares on the screen, but you can do it yourself. 6.3 squared plus 9.6 squared plus 12.2 squared plus 12.3 squared plus 10.3 squared plus 12.1 squared plus 10.3 squared plus 8.4 squared plus 9.2 squared plus 4.3 squared. And you should get something like 964.26. So knowing this, we can calculate the standard deviation. So we have the square root of 964.26 all over the number of terms, which is 10, minus the mean squared, so 9.5 squared. So this would be equal to the square root of this over 10 minus 9.5 squared. So I get the square root of 6.176. And so this is equal to around 2.49. So we have a mean of 9.5 and a standard deviation of 2.49, really. So we need to comment on whether there are grounds for investigation. If over 10 micrograms per liter is deadly, I would say yes, because the mean amount is within one standard deviation of the level deemed dangerous. Actually, it's like closer than one standard deviation. So there are further grounds for investigation because the standard deviation is like oh, this water could actually be at this level, because all of the values deviate at around 2.49 around this mean. So yes, there are certainly further grounds. So yeah, that was all for the speedrun. I hope you enjoyed it, and I hope to see you in the next one.